My gosh. Okay. I'm just going to wait a second for people to file in. There's still some people coming in the back. No? Okay, I'm not allowed to. I have to keep going. Sorry. So, thank you all for coming to lecture number 2. What I want to talk about today is quadratic forms and their connection to modular forms explicitly. This was discussed in great detail, in some sense, by Professor Elkes, who wrote down the theta series associated to a quadratic form. Okay? So for his purposes, he was interested in understanding the number of short vectors of a quadratic form and the relation between the lattice that he has and the space of modular forms. And so he's able to use this connection to great effect because the space of modular forms the theta series lives in was small, and one could understand explicitly generators for this and sort of work things out. Okay? I'm going to have a slightly different perspective, but I still would like to talk about theta series. So I'm going to start with a positive definite quadratic form, q of x. Okay. So it's positive definite quadratic form over the integers. And just to jump right in, I'll define the theta series of this to be a generating function for the number of ways of representing the number m by the quadratic form. Okay, so this is positive definite. So in particular, this means that r sub q of m, which I'll define to be the number of solutions, x in z to the n, so that q of x is equal to m, is finite. Okay. So I define the theta series to be the sum over all numbers, which could be represented by the form, which are now non-negative numbers, r sub q of m, if you write it with q's, you'd write q to the m. Just to be extra clear, I'll say e to the 2 pi I mz. Okay, so this is the same thing as q to the m if you take q to be e to the 2 pi I z. Okay. This is the definition of a theta series. And as was pointed out yesterday by Professor Elkes, this is a function with a lot of symmetries. Okay? So in particular, it has some symmetries of taking z, going to z plus 1, because it's a Fourier series. So just because this is periodic, it also has symmetries of the kind where z goes to something like minus 1 over mz. So this is just because it's a Fourier series. And this follows from Poisson summation. So the idea is that you have some sum. Here we have a sum of representation numbers against this. You can re-express this as a sum over a lattice of all vectors. So I guess the idea is that the theta series q of z can also be thought of as a sum over all vectors x in z to the n of e to the 2 pi I q of x z. Now when you see this, can people read that? So when you see this, this is now a very symmetric kind of object. This is a sum over a lattice, okay, which is the kind of thing they use Poisson summation for. And this function here, e to the 2 pi I q of xz, this is a quadratic function. This is a quadratic Gaussian. Okay? And we know that the Gaussians are self-dual under the Fourier transform, and so it's not unreasonable to expect that if I take a sum of some self-dual function, then it's related to, in some nice way, the sum of its Fourier transform, which will leave the function basically invariant. Okay? So that's all I can say about this because I have time constraints. But these two symmetries together, okay, and modifications of this, there are references for this in the notes, by the way. I'm not really cheating. you can really work this out, but it's a little bit painful to get exactly the group of symmetries of this function. So the group of symmetries is usually called the theta group. What we care about in sort of the modern language is how to say this in terms of modular forms. Okay? So the theorem is that this theta function, q of z, is a modular form. I'll say what that means. Of weight k, which is half the number of variables, some level n, and some character chi, which is a quadratic character, so chi of something is equal to, it's going to be a plus or minus the determinant of the form over that thing. So to be a modular form, f is a modular form with, let's say, invariance k and chi as above. Okay? If f of az plus b over cz plus d, so these are linear fractional transformations acting on the upper half plane, is equal to cz plus d to the k over 2, to the k, sorry, times f of z, and then possibly times some multiplier system, epsilon cd, bless you, multiplier system. Okay. And so I should tell you what kind of symmetries I have, where A, B, C, D are in this congruent subgroup gamma naught of n. So this is a subgroup of finite index in SL2Z. I'm sorry? Oh, yes, thank you. Yes. Chi of D, some character of D, thank you. Where this is, these are all the elements, so these are defined to be the elements of SL2Z, SL2Z, sorry, such that, so A, B, C, D are congruent to some upper triangular matrices modulo n. So what this is doing, this is defining for you, the n defines for you a congruent subgroup. So note, just by virtue of this map to z mod nz, that gamma naught of n, well, let's say it this way, the index of gamma naught of n in SL2Z is something you can explicitly calculate, and it's finite. Okay? So it says it roughly has the symmetries of SL2Z, but you have to look at this subgroup to really see them. And chi here is a character mod n, and so this is going to be a character which is going to take the entry here. It's going to be a character on that. Okay? So if we look at the determinant of this mod n, then this is really, the determinant is 1, and so AD is equal to 1 mod n, and so this is really a character on that diagonal. So it's a little bit complicated to explain all at once what a modular form is. So this is not the complete definition yet. These are just the symmetries. The other condition that you need is that it's going to be a holomorphic function. Okay? So it transforms in this way with respect to some multiplier system. Oftentimes the multiplier system is trivial. We don't see it. If it's half integral, then you have to be a little bit careful about the multiplier system. Okay? So where f of z is a holomorphic function from the upper half plane to the complex numbers, which is also holomorphic at all boundary cusps. So I have to explain what this means. So the idea, I'm going to flip back to the other transparency so that we can see what's going on. The idea is that this group gamma naught of n is acting on the upper half plane by linear fractional transformations, and you can write down a fundamental domain for that action. You can do this because SL2Z has an explicit fundamental domain that you can see, and this is something of finite index in that, so it's going to be a finite number of copies of translates of that fundamental domain. So, for example, suppose the upper half plane modulo gamma naught of n happen to look like so this is for SL2Z, and this is maybe something, if it was index 3 inside of it, happened to look like this. Then this is in the upper half plane, and I can move every element of the upper half plane by these transformations into one of these three regions. Okay? So then the feature for modular forms that's important are these boundary points. So here I have a boundary point, and up here there's also a boundary point at infinity. So I think of there being a P1 of Q sort of encircling the upper half plane. And these are called the cusps. And so the cusps are very important for the theory of modular forms in lots of ways. Here's the first way, is that I'm requiring somehow that the function be holomorphic as it approaches these cusp points. This can be made precise if you compactify this and look at the associated Riemann surface. Then you really have charts. Here I haven't really been clear about what my charts are, so it's not so clear. But hopefully this at least makes some sense to you. So to be holomorphic at a cusp means at the cusp infinity, let's say, just say this, holomorphic at infinity, meaning the one up there, is the same thing as saying that the Fourier expansion of the modular form f is a power series in Q. So it means that if you think of Q as being a chart at the neighborhood of infinity, then it's holomorphic in this sense. And you can make a similar definition for all of the other cusps if you need to. In general, there are finitely many cusps, and one needs to take them into account, but that's the idea. Okay. So just some more quick comments. So there's a subtlety here about the multiplier system. So let's say note, since the weight is equal to half the number of variables. Okay, so the weight of the modular, the theta function, is half the number of variables. We need to be extra careful if n is odd. Okay. And what I mean by this is that they have to take square roots, the square root of cz plus d. You have to be careful as to what that means. And there's some multiplier system that enters in that is called, so there's called a theta multiplier. System epsilon CD, and there is the claim is that there is some choice of multiplier system so that this makes sense. Okay, so the definition is hiding this multiplier system, but if the weight is even, then I don't see the multiplier system at all, and I just get a modular form in the sense that I wrote down there, with you just cover up the epsilons. Okay, so this is one of the reasons that half integral weight modular forms are harder than integral weight, is because you have to take into account these multiplier systems. This has lots of consequences for the theory. If you know something about modular forms already, this means you have less Hanke operators than you would expect. Okay? It makes your life a little bit harder. And also the connection with geometry is a little bit harder. Okay? So in general, when you see theorems about quadratic forms and explicit numbers of representations, they tend to be things about even numbers of variables. And this is the reason. Okay. So the space of modular forms, so let me just say some facts about modular forms. Right, okay. So the first fact is that the space of modular forms, so I'll write as mk n chi, this is the space of modular forms. Modular forms with the invariance n, k, the weight, the level, and the character, is a finite dimensional vector space over the complex numbers. Okay? It's a finite dimensional vector space over C. And so once you know that your theta function transforms in a certain way, you can try to ask what's the dimension of this space and how does my theta function sit inside of it. Okay? This was used to great effect for unimodular lattices in small rank. Particularly, you can show that you can understand exactly what the short vectors are by looking at their theta series. You can also classify that unimodular things have to be divisible by, have dimension divisible by 8, and lots of other things. But the basic idea is that you exploiting the dimension of the space to extract information about the modular about the lattice. Okay. So the second property is that there's a natural decomposition of the space of modular forms, mk of n chi, into two parts. So mk n chi is a direct sum of what I'll call the Eisenstein space and the cusp space. So these are called Eisenstein series. And these are things that you can explicitly construct based on the cusps. And these are called cusp forms. So let me just define what this is. So cusp forms, these are things that vanish at all cusps. So that's a definition of a cusp form. Okay, so the subspace of functions that vanishes at all of these finitely many boundary cusp points, those are called cusp forms, and there's a natural complementary space to it in this, and there's even an inner product that shows what this complementarity is. Okay. Eisenstein series are functions, sort of conversely, that have to take values at the cusp, because the cusp forms don't, and if there are modular forms that take values there, then you have to see them here. And these can be explicitly with values at the cusps. Okay. So, bless you. Okay. So as an example, you can write down an Eisenstein series of weight k as a sum, an explicit sum over elements of CD not equal to 0, 0 in Z2 of 1 over CZ plus D to the K. So this is an example of an Eisenstein series which vanishes, which has value at the cusp infinity. So these are things you can really write down. Okay? You can compute in terms of this, this sum. You can unwind it in such a way that you can compute its Fourier expansion. Maybe I should write down what its Fourier expansion is. It's a little bit hard because I want to shift this paper up, but I'm going to have trouble. So in particular, maybe I'll just do that. So E sub k of z can be written as a Q series. So it's 1 plus, I'll write some constant, times the sum of divisor sums, k minus 1 of m, q to the m. M is greater than 1. Greater than or equal to 1. Okay? This is a theorem. Not quite true. But I put a constant in here, so I'm normalizing it. So it's this is some capital K times this. Thank you. Right. Thank you. So up to some constant, this looks like this. Is absolutely correct. Okay. So now the theorem is true. Okay. And then the idea of this, these are explicit constants. Right. These are explicit. And so the idea of this is that you can actually sort of get a feeling for how the Fourier coefficients of this Eisenstein series grow. Okay, so the nth Fourier coefficient grows like this is the divisor function. Okay, so I should write down at least what that is. So maybe I'll do that here, where sigma sub d of m is defined to be the sum over all divisors. Oh, I really shouldn't have used d here. Let's just say k minus 1. This is the sum over all divisors, d dividing m, which are bigger than 0, of d to the k minus 1. This is the divisor function, and you can see that this means the Fourier coefficients are about the size of d to the k minus 1. So they're at least that big. Okay, that's what the main term is. In general, if you look at different Eisenstein series for different cusps, they may grow or get smaller, but in absolute value, they'll roughly be about this size fairly often. Okay, so you can sort of say the size of an Eisenstein series coefficient. Okay. So the third thing that I want to say is about asymptotics. So the idea is that Eisenstein series and cusp forms have different growth rates of their Fourier coefficients. So we've already seen that the Eisenstein series, or at least one Eisenstein series, has coefficients that are roughly the size of m to the k, where the mth Fourier coefficient is about m to the k minus 1. I'm sorry. So if you have an Eisenstein series, so far, in general, you know that the Eisenstein series, let's say a sub e of m, meaning the mth Eisenstein coefficient, can be as big as, so I'll say is approximately equal to, meaning that it can be as big as, but it may not always be, but you can't avoid something of this size, m to the k minus 1. It's a very imprecise statement. You have to really look at a given Eisenstein series and see what's going on, but for this one you can see that that's true. And in general, if you have a cusp form, so I'll say a sub c of m for a cusp form, is always bounded by an absolute value. This is also absolute value. Is always bounded by m to the k over 2. Some constant times. I'm always a subconstant. This is some constant here. So what this means is that the cusp forms, so in general, so if k is large, the Eisenstein coefficients dominate. Cusp coefficients. Okay. So the main term in some asymptotic expansion comes from the Eisenstein series. This is a really important fact, and this can be exploited in the theory of quadratic forms to prove asymptotic statements for the representation numbers of a quadratic form. Am I doing that fine? Okay. Great. So, so example, let's say that n is equal to 5. Okay, so I have a quadratic form in 5 variables. So q is equal to some quadratic form in 5 variables. Okay. Then this means that the Eisenstein coefficient, thank you, the Eisenstein coefficient should be approximately as large as m to the 5 minus 1, no, 5 over 2 minus 1, which is m to the 3 halves. Okay. And this is a sub e of m. And the cusp coefficient of any cusp form should be approximately, or should be bounded by, this is an absolute value, should be bounded by some constant times m to the k over 2. So this is 5 halves is k, and I take half of that, so this is 5 fourths. And you compare these, and you see that 3 halves is definitely bigger than 5 fourths. And so that means that if you take theta series, so if you look at theta sub q of z, and you write it as an Eisenstein series plus some cusp form, then this means that this Fourier coefficient is going to be bigger than this Fourier coefficient in most places, and the representation number, r sub q of m, which is the sum of these two coefficients, a sub c of m, this grows approximately like m to the 5 fourths, and this grows approximately like m to the 3 halves. And so if I could say that the Eisenstein coefficient is non-zero, okay, or roughly this size, then I would know, and positive, okay, but there's a positivity condition throughout, then I would know that m is represented by my quadratic form. Okay. Oh, that's really embarrassing. Thank you. That's much better. So this is less than or equal to. Okay. So the idea is that if we can show that a sub e of m is greater than 0 and of this size, as m approaches infinity in some way, we know that r sub q of m is greater than 0. So in particular, this means that m is represented by the quadratic form q. This is an asymptotic kind of a statement. For sufficiently large numbers m, you'd like to use the asymptotics of the modular forms to tell you if m is represented. So the only trouble with this strategy is that I don't necessarily know anything about E or C. Okay? And so I need to get some information about that to implement this strategy. And that's what I want to talk about now. Okay? But this is the way that, that people prove asymptotic theorems about quadratic forms. The history of this is that this was first proved by the circle method. This is really an outgrowth of the circle method. Okay? By Tartakovsky, in 5 or more variables, he proved this kind of a statement. If m is sufficiently large and locally represented by the quadratic form, then it's globally represented. Okay? For sufficiently large m. This was then refined by Kloosterman by doing some things with the circle method, by refining the circle method in a certain way. And he was able to extend this to case of 4 variables. If you're locally represented, and there's an additional condition there about being anisotropic, so you have to be careful about anisotropic primes. But he showed roughly a similar statement. If it's locally represented and you have bounded numbers of divisibility by anisotropic primes, then it's globally represented. And then for case of 3 variables, things get even harder, and you have to use really the full theory of modular forms in weight 3/2. And that's beautiful work due to Duke and Schulze-Pillow using the idea of Ivanich to bound Fourier coefficients of half-integral weight cusp forms. Okay. So that's sort of a summary. N greater than or equal to 5 is Tartakovsky, which I'm definitely misspelling because it's a Russian name. N is equal to 4, so this is asymptotic results by Kloosterman. These are both by the circle method. The circle method is now, in terms of these results anyway, you can now see everything that they saw in terms of the theory of modular forms. Okay, so that's what we're seeing here. And n is equal to 3, using ideas of Ivanich, which is really very substantial work in convexity breaking for these half-integral weight square-free Fourier coefficients, and work of Duke and Schulze-Pillow. One has similar asymptotic, there are, I'll just say, some asymptotic results. Of this kind. Okay, because I don't really have time to get into the details of exactly how one says it. But just so you're aware. And this is really, the less variables you have, the fancier things get. Okay. So what I'd like to do is try to explain what you know about the Eisenstein series. Okay? So the Eisenstein series really encapsulates a lot of information. Okay? So by this I mean the Eisenstein series in the decomposition of theta as an Eisenstein series plus the cusp form. Okay? So I mean this particular Eisenstein series. So if I write E of z is equal to the sum m greater than or equal to 0, a sub e of m, q to the m, then there's a theorem of Siegel which gives us a lot of information about this Eisenstein series. Okay? So in particular, it describes exactly what the mth Fourier coefficient is. Okay? And it describes it in 2 possible ways. So either you can look at the genus of the quadratic form, which we defined last time, and you can sum overall classes in the genus. And you can sum, so we're taking an average over the genus, and I'm going to weight the average of the representation numbers, r sub q prime of m, by the number of automorphisms of each quadratic form. Okay, so there are finitely many classes in the genus, it's a finite sum. And I'm using this weighting factor, so to make it a weighted average, I better divide out by what that weighting factor is. It might not be 1. Of 1 over this number of automorphisms. Okay. So that's one way of describing explicitly what this Eisenstein coefficient is. And that's kind of nice. So it's an average over the genus. So in particular, this gives local information. Okay. Because it gives you an average over the genus. But you can really get explicit local information because there's another way of writing this as a product over all places. These are places. Of what are called local representation densities. So these are numbers, and this is defined to be, let me just say, local representation densities for right now. And the important thing about these numbers, which I'll write down in a minute, is that they only depend on understanding the quadratic form locally at the completion v. Okay, so locally over the p-adic numbers for every place, and also at infinity. I'm sorry? Or minus 1, I'm sorry. Or minus 1. I don't want to discriminate. Okay. So explicitly, these local representation densities, beta sub vq of m, is defined to be a limit over open sets containing the number m. So what I'm going to do is I want to measure how many solutions I have mod powers of p. Because I really want to take the volume of the p-adic number of solutions or the volume of the real number of solutions, q of x equals m. Okay, so what this gadget is going to do is going to try to take this. So I'm taking this over open sets approaching m. Okay, so that's what I mean. So u is approaching m, shrinking, of the volume of q inverse of u. Okay. So it's a number. The quadratic form is a map to a space. And then this is over the volume of u. Okay. So let me be a little bit careful here, where q is a map from the space of 1 by n by 1 matrices over zp to I guess I want to say the symmetric 1 by 1 matrices over CP. Okay. So what I'm just saying here is here I'm taking some vector x, okay, and I'm sending it to x transpose ax. And that's what's happening here. I'm writing in this sort of rather funny way because there's a generalization of this where you're representing not numbers but other quadratic forms, and in that case you have n by m matrices here, and you end up with a symmetric m by m matrix. And this formula still holds in that case. So if it happens that V is equal to a p-adic place, then you can re-express this local density as a limit of mod powers of P by choosing a certain family of open neighborhoods going towards U. So the family given by powers of P, the natural one for that filtration. So here you can think of a limit as alpha goes to infinity of the number of solutions q of x is congruent to m mod p to the alpha over the expected number of solutions. So this is a hypersurface in n-dimensional space. And so this is p to the alpha is the space to the n minus 1. So this is some explicit thing you can compute. And there's some limit we're taking here. But the nice thing about this is by Hensel's lemma, this limit is eventually constant. And in fact, if p does not divide the, let's say, 2 times the determinant, or the level of the quadratic form, you can take alpha to be equal to 1. Oh, I'm sorry. So if you're at away from finitely many primes, okay, then you can just count the solutions mod p, okay, and that will allow you to evaluate these densities. So this is really beautiful, really, really amazing result, because what it says is that the Eisenstein series encapsulates all of the local information about the quadratic form. I'll say that again. The Eisenstein series tells you everything that you know about the genus of the quadratic form just by looking locally. And so you don't really need to know anything about the quadratic form over Z. You can just look at local invariants of the form and you can compute its Eisenstein series of any theta function in the genus. Because the Eisenstein series is the same for every theta function in the genus. That's a really strong thing. And this also controls the asymptotics of the number of representations. So useful things to know are if one of these beta v's is 0, that means that there's a concurrence obstruction to m being represented. And if there's a concurrence obstruction, that means that there's no way that m is represented, but that also means that the Eisenstein coefficient is 0 because it's a factor in an infinite product. Okay. So there's a lot of things you can say about these, but But the most important is that it's local and it's easily computable. So let's say I have 15 minutes. This is going well. So let me talk about a simplification. So if the class number of the quadratic form, so this is defined to be the size of the genus of the quadratic form, it's the class number, is equal to 1, then what does this formula give us? Okay. So then this tells us that the Eisenstein series coefficient is equal to some weighted average. How do I say this? This is some weighted average of Q prime in the genus of Q, of these things, over the sum of Q prime in the genus of Q, of 1 over the number of automorphisms, R sub Q prime of M. But now I just have one class in the genus. So in this case, I just get R sub Q of M over the number of automorphisms of Q. Okay, so here I'm using the class number as 1, right in here, over 1 over the number of automorphisms of Q. And this is a really amazing thing, because now I can cancel, and I get exactly the representation numbers. So what this means is that the number of ways of writing M in terms of a quadratic form can be seen purely locally and can be computed purely locally in terms of just these local densities. Okay. So this is a really nice fact. This justifies why we love class number 1 forms. So as an example, the quadratic form x squared plus y squared plus z squared plus w squared is a class number 1 form. So let me check this up. Has class number 1. And so in particular, what that means is I can use local representation densities to compute the number of ways of representing a number by this form. Okay. So this means there's some explicit formula that you can give in terms of local information. And there's a formula due to Jacobi. I don't know if people know this formula, but it's beautiful. So this is 8 times the sum of the divisors of M, which are bigger than 0, which are not divisible by 4. 4 does not divide D. This is due to Jacobi. So if I have time, I'll try to prove part of this formula using this formalism. But let me say something else before I do. Okay, so this is a really explicit formula, right? If you pick any number, you can easily compute what the side is, and that's a lot easier than looking for vectors in some ellipsoid of a certain length. Any questions? So the point is that you have a lot of information about the quadratic form in terms of modular forms, and you can encapsulate a lot of the information in terms of the local information, either in terms of asymptotics in general, or in terms of explicit formulas if you have class number 1. Okay. So there are some generalizations. So we did simplification, generalizations, which is that you can talk about representing. So there is a Siegel formula. So there exists a Siegel formula for representations. Quadratic forms by other quadratic forms. Okay. In particular, what it does is it tells you exactly the same kind of thing, but now I have a quadratic form R sub Q, and let's say there's some Q prime, Q tilde, R sub Q tilde. This is some quadratic form over the number of automorphisms. This is a Q prime, again, in the genus of Q prime, over a sum of 1 over the number of automorphisms. Okay, so again, if you just weight the number of representations of a fixed quadratic form over the genus of your large quadratic form, then this is again something that you can write as a product of local densities, beta QV, but now representing some fixed, smaller quadratic form. Okay, so here, R sub Q prime of Q tilde, sorry, is defined to be the number of representations of Q tilde by Q. And you can think of this in various ways. You can think of this as this: if this corresponds to a lattice L, and this corresponds to a lattice L tilde, then this lattice, if Q represents Q tilde, then L tilde embeds inside of L. And you can think of this in terms of numbers. If I represent the number 5, that means that there's some vector of length 5 in my larger quadratic lattice, and that defines an embedding of 5x squared into the larger lattice just by taking that vector and extending it. So that's the idea here. So this is purely something in terms of quadratic forms. I haven't said the word modular form here. Okay? But if you did say the word modular form, then you could put this as the Eisenstein Fourier coefficient of some form Q tilde. But this is now the coefficient of an Eisenstein series of some symplectic modular form, sp2n, some gamma naught of n, which sits inside of the symplectic group. Okay. These are called Siegel modular forms. Okay. And because he was the first one to study them, and he studied them exactly for this reason, okay, because he had this theorem and he wanted to understand it in terms of modular forms. If you actually work with them, they look a lot like regular modular forms, but now you have a block diagonal decomposition, A, B, C, D, for your matrices, and this says that that lower left block is congruent to 0 mod n. Okay. So that's a generalization. You can also do the same thing over a totally real field. You get something called a Hilbert modular form, and the theorems of the same kind, exactly the same, hold there. Okay. Okay, so I have 5 minutes left. I have 5 minutes left, right? Great. So I want to say 2 more things. One is an example of this generalization. So it's called a mass formula. Okay. And here we'll suppose that Q and Q tilde, the form that you're representing and the form you're using to represent it, have the same dimension. They have the same number of variables. In this case, what happens is that you have a formula exactly the same as before. So you have some formula for the number of representations, R sub Q of Q tilde, so this is Q prime, for Q prime in the genus of Q. So it's over the number of automorphisms. I'm just rewriting the same thing, so you don't need to copy it down. 1 over the number of automorphisms of Q prime. So we have a formula for this in terms of a product of these local densities, beta VQ of Q tilde. Now, if this is of the same dimension as this, then in order to, if I embed one inside of, if I embed this inside of the other, so you take Q tilde in the genus of Q, then if I have a representation, then that means that I have an actual isomorphism. And so the point here is that, bless you, that the number of representations is exactly the number of automorphisms of the quadratic form. So maybe I should take Q tilde to be equal to Q.
Sorry.
Yes?
So when you say that Q tilde is represented by Q, are you saying that the set of vectors represents
That's a consequence. That's a consequence, but it really means I can take Q tilde and embed it as a sublattice inside of the lattice of Q. Okay? That's what it really means. And so in particular, it'll represent all the same, they'll represent some subset of that numbers. Yep, that's right. So if you take Q tilde equal to Q, then this means that R sub Q prime of Q tilde is equal to 1 if q prime is equal to q tilde, and 0 if q prime is not equal to q. So what I'm doing, I probably should have written this over here. Say it again? Oh, it's the number of automorphisms, sorry. Thank you. Because if I'm representing a form by itself, that's the number of automorphisms. Okay. And so what this means is that I have a formula for 1 over the sum in the genus of 1 over the number of automorphisms as a product of these local numbers. Okay. And this number here is defined to be the mass of the quadratic form. And you can use this to get a handle on the class number of the quadratic form, but I don't think we have time to say that. I want to do an example. It'll take me 5 minutes. Is that all right? Okay. So you can use things about the mass. One of my projects is related to using the mass to understand the class number. Okay. So I'll just state the fact. Since the number of automorphisms of q prime is bigger than or equal to 2, you always have 2 automorphisms, this means that the class number, the mass, is less than or equal to the class number, is mass of q, the class number of q over 2. So if the mass of q, which is again a purely local quantity, goes to infinity, then so does the class number. And if the mass is bigger than something, then the class number is also bigger than something. In particular, you can tell if you have class number 1 or not. Okay. So that's one of the projects for my group, is to actually implement this in over certain fields and try to characterize the number of dimensions in which you can have a class number 1 form. So the second thing I want to do is just to give an example of Siegel's theorem when q is x squared plus y squared plus z squared plus w squared. Okay? And I'm going to skip some steps. But I want to do this so that you understand this is a real computation and you shouldn't be afraid of it. Okay. So in this case, what I want to do is, we know the class number is 1. So I want to compute all of the local densities. So the real density, which is beta infinity, or if you want, beta of -1, okay, of m, is taken to be some limit, okay, which you can work out. And I can do it? Okay, so this is the limit as I take some neighborhood, let's say m minus epsilon to m plus epsilon, which contains the element m. This is the real limit here of the number of solutions of the volume of q inverse, this is u, of u. This is some shell of an ellipsoid. That's how you should think about this, in 4 variables. Divided by the length of this, which is 2 epsilon, and we're taking the limit as epsilon is going to 0. Now you can work out what this is if you know the volume of a force sphere is equal to pi squared over 2 times r to the 4th. So I'm going to skip some steps here because I want to finish. So you can work out that the local representation density at m is equal to pi squared times m. So it's not hard to do. It would take me 3 or 4 more lines with just this formula. So that's something that you can explicitly compute. And my goal is to multiply them all together and get an answer. At some prime place, beta p of m, and let's say p is not equal to 2, because 2 is a little bit special, then this is equal to the number of solutions. So here we can take alpha to be equal to 1. This is the number of solutions. Q of x is congruent to m mod p over the expected number of solutions, which is, which is p cubed. And you can work out what this is by a Gauss sum. It's not a very hard computation to work out the number of solutions. So let's take, let's say, m is not congruent to 0, mod p, then the answer for this is it's p cubed minus p over p cubed. So the local density at p looks like 1 minus 1 over p squared. And that's for all primes except for 2. So you've computed all but one factor. When p is equal to 2, then it's a little bit harder. I have to actually take this limit a couple of steps up. Beta 2 of m. I'm going to assume now that m is not divisible by 2. And it's enough here to take the limit when alpha is equal to 3. Okay, so you can always lift solutions mod 8 to p-adic solutions if a sum of squares. And so this is equal to the number of solutions of this thing modulo 8 over 8 cubed. This is by Hensel's lemma. I know this is enough. And the answer here is you can just use a computer to count. I mean, m can only be 1, 3, 5, or 7 mod 8. Right? For each of them, you can count the number of solutions mod 8. And this is always 512. Okay? So I'm just counting over 8 cubed, but 512 is 8 cubed, so that's 1. Okay. So now I've explicitly computed all of the representation densities for things that are not divisible by p at any prime p. Okay. So now I'm going to multiply them together. This is sort of the intimidating step. So this means that the product over all places of beta v of m, okay, and let's take m to be equal to 1, because that's the only number that I know that's not divisible by any primes p. Okay, so that's the only place this formula is going to work. The only positive, definite, positive, okay. Natural number, thank you. Okay. So this is equal to pi squared times 1 times 1. So this is from the real numbers. This is from 2, and times the product over all p bigger than 2 of 1 minus 1 over p squared. Okay. Now I have to multiply together this infinite product, but hopefully you've seen that zeta of 2 is the product of 1 over this product, 1 over p squared, over all primes p. And zeta of 2 is also pi squared over 6. So this product that we've written down here, I can compute by taking 1 over this and killing the factor at 2. So this means that this product over v of beta v of m is equal to pi squared times 6 over pi squared times the Euler factor that I had to take away, and p equals 2. So I'm using this fact here together with the killing of the Euler factor, which is 1 over 1 minus the prime 2. This is 4. So this is pi squared times 6 over pi squared. Those cancel. Times what is this? This is 1 over 3/4, which is 4/3, which is equal to 8. So what we've proved here is the number of ways of representing 1 as a sum of 4 squares is equal to 8. Which is actually a very cool way of proving this. Okay? But not the fastest way. Okay? So, I'm sorry? I'm always going to cheat when I use this formula. That's right. Whenever you use this formula, the things that you get as infinite products will always be special values of Dedekind zeta functions or their twists to the quadratic character. The mass formula as well. Okay. So let me just make a comment about this, and then I'll be done, because I'm representing 1. That's not so interesting. So you can actually, if you take m to be equal to p, then you have to adjust only 2 things in this formula. Okay? The first thing is that the factor at infinity goes from pi squared to pi squared p. Okay, so it gains a factor of p. And the factor at p, you can work out, again, with the Gauss sum. This is 1 plus 1 over p times 1 minus 1 over p squared. Okay? So here we've adjusted by multiplying by p. And here we've adjusted by multiplying, so the old factor was this, by 1 plus 1 over p. So what this means is that the number of solutions, r sub q of p, is equal to p plus 1 times the 8 that we had before. And if you do this for all square free numbers, then r sub q of t, so p is not 2. Okay, be careful. And this is square free. 2 does not divide t, is equal to 8 times the sum of the divisors of t of d. And that's not quite Jacobi's formula, but it's close enough to hopefully feel as though this technique gives you a lot of information about quadratic forms. Square factors are harder because you have to go higher in your local density computations. Okay? Well, that's sort of an explicit example, and I'll come back to the Ziegelway formula, at least in some sense, in lecture 4, where I try to give a more automorphic interpretation of this theta series in terms of the Weyl representation. Thank you.